So step 1, mark on the tension in the system. We know the tension is the same top and bottom. And we are going to look at F equals ma at both P and Q. So at P, if we resolve horizontally, the horizontal forces we've got are tension, that blue arrow to the right, this blue arrow here, tension pulling it right. We don't have any forces to the left, okay? The mass or the weight of the particle down is irrelevant because we're looking at the left-right motion. There's no friction, it's a smooth table. So just the tension is equal to the mass times the acceleration. Here, what are we looking at? We've got the weight. The weight, which is mg, which is giving us the vertical force down. So then we're going to look at resolving vertically down. We've now got our two different equations which relate to T and A, and we're going to solve them simultaneously. So if we add them together, that will cancel out the T's, and we get 0.6 G is 1.4 A. Solve that for A, which is 0.6 G over 1.4, which is 4.2 meters per second squared, as asked in the question. We then want to know the time taken by P to hit the pulley. And there's two parts to this. One is the initial acceleration, i.e. when Q's moving down, or Q's accelerating down, P's accelerating across. And then Q's going to hit this base here, and then P's going to keep moving at a constant speed. Why does it keep moving at a constant speed? Because there's no friction, so there's no deceleration. Okay? And we know an object moving at a constant speed will continue to do so unless acted on by an imbalanced force. And when it's sliding there's actually no forces horizontally acting upon it. So let's work out what speed it gets up to before Q hits the surface. So in that initial acceleration, we know the acceleration there. We started at rest. V we want to know, and later we're going to come back, so we're going to need to find the time for this as well. And S, we know it moves 0.4. So then we're going to use V squared is U squared plus 2AS and solve that for V. And for now, let's keep it as an exact answer. So we know, whilst it moves at 0.4 meters, it gets up to a velocity of 2 root 21 over 5. And then we want to look at, well, how long is it going to take travelling at that velocity there to hit the pulley? Time is the thing we don't know. And now we've got to work out what's the distance it needs to cover before it hits the pulley. So if we look back up here, it's 1.5 in total it's got to move. But remember, when this has moved 0.4, this has also moved 0.4. So what will it have left? It's going to have the 1.1 meters left before it hits the pulley to cover. So we're saying, okay, well, if it's travelling at this speed, which it will be after Q's hit the ground, how long will it take to cover that distance? I'm going to do S equals ut plus a half at squared. It's pretty straightforward because we don't have an acceleration. So it's just S equals ut. Solve that for time. Okay, so we know the time from after Q hits the ground until the particle hits the pulley is 0.6 seconds. And then we need to know, well, how long does Q take to hit the ground? And then we've got the two parts to it. So we've got the initial acceleration, and then we've got the constant speed. So we're using this info again. S is ut plus half at squared. In this case, we don't have an initial velocity, so ut cancels out, but we do have an acceleration. So then we can work out that t is 0.436. So now we want to know what the total time is for part 1 and part 2. So part 1 is that initial acceleration, then Q hits the ground, then the thing just keeps gliding along because there's no friction. So it gives us 1.0 seconds to 2SF. And then we've got what are our limitations of the model. And we've got rope being light, rope being inextensible, pulley being smooth. Okay, all of those are assumptions, and all of those will affect the outcomes we get from our model. Okay, so I've said in reality it would have a mass, and obviously that would affect the acceleration because there's a weight of that rope.